Hi, everyone, and welcome to our final session at the Docker Best Practices track. My name is Christy Howard. I'm a software engineer here at Docker, and I'm actually really excited about this talk because this talk is about how the Docker SaaS team actually moved to Docker EE and how we use Docker at Docker to deliver Docker. And Brett and Marcus actually were part of the team that helped set up EE, and I'm a developer on the teams that actually use or were the internal customers of the EE solution. So Brett is an infrastructure engineer at Docker, and Marcus is an orchestration manager at Docker. And please give them a very warm round of applause and a big welcome.
Thank you. Yeah, thanks, Christy. Like she said, this is really cool for us. It's been a long time in the making for our teams, and we've spent a lot of time moving all of our infrastructure for the SaaS services over. And like she said, I work on the infrastructure team. Marcus, who's joining me, actually worked on the team that ran Hub, and he is actually now in charge of the team that builds the orchestration product in Docker EE. So it's a cool mix of people for this. So real quickly, the talk is Docker on Docker. We're going to talk about basically where we were, what it used to look like for us, how we moved to Docker EE, what we learned during that process, and how we're making Docker EE better through that process. So to give you a quick idea of what SaaS at Docker really means, basically we run Docker Hub, Docker Store, and Docker Cloud. So if you're unfamiliar with those, Hub is where you push and pull images from by default. Store is where you can get certified content, including images and plugins. And Cloud is a Docker management platform. To give you an idea of the scale, we do about 1 billion polls a month, and that's only increasing every day. About 500,000 automated builds on Hub, and about 5,000 requests per second, just to give you an idea. And let me tell you a little bit about our philosophy running SaaS at Docker. So obviously the first thing is high availability. All of you want to be able to push and pull your images all the time without us being down. That's kind of important. But more important than that for us is actually having our infrastructure be self-healing. So it's really easy to spin up 3 managers and say, okay, I now have high availability. That's a good start. The problem is what happens when you lose a manager. Does someone have to go in and replace it manually, or does it happen through automation? And given that we only have 3 people on our team, automation is critical for us. Next principle is self-service. So our goal on the infrastructure team is to provide our developers with a layer that they can build on top of. We shouldn't be in the critical path for them. We shouldn't block their deployments or anything else with them waiting for stuff from us. And finally, the big thing for us is if you build it, you own it. So our development teams are responsible for their application from actually building it to running it and to being on call for it. And likewise, the infrastructure team is responsible for building and being on call for infrastructure. So let me tell you a little bit about where we were. So in the past, basically what we provided for our teams was we just gave them a group of Docker hosts. They were running Docker Engine, and we gave a set of hosts to each team. And because we don't give them SSH access or anything like that, we gave them TLS certs for the Docker API, which lets them securely connect to them and do deployments. On top of that, we also provide a set of services that are our responsibility, centralized logging and metrics, and then also service discovery and routing. So when our developers deploy a container, they know that they get everything that they need to run that container. So like I said, logging, metrics, and routing. And I'll hand it over to Marcus to tell you exactly how they use that infrastructure.
Thanks, Brett. So, as I said, as Brett is talking about what we have for Docker and how we're using Docker EE, dog fooding for Docker is not a new thing. We have been dog fooding Docker on the SaaS side since 2013, and I went back to some of our older components and found Docker files dating back to December 2013, roughly. And if you look at the timeline of the Docker project, that's as early adopters as we get. And with being early adopters of the project, we have been benefiting from Docker for a long time. And for that is, well, our environment is fully containerized and has been fully containerized for the last, say, 4 years now. So for a developer on the team, everything that we run is in containers. That's the only thing we run in Docker SaaS. And not only we run everything in containers, our only interface with the host is via the Docker API. So that provides us with a very narrow entry point to the system and allows infrastructure to control who has access and how that works. Everything is done through the Docker API. No one has any SSH access to any of the boxes. So we know that the foundation the infra is providing for us has been vetted and stable, and we just work on the layer above that. At least that's the practice. In reality, for us being early adopters of Docker, we have evolved together with the Docker ecosystem. So we have multiple teams responsible for different parts of the service, and you can see the evolution of the teams and the tools that we use throughout those years. So if you go to some of our earlier and simplest deployment tools, it's just a bash script, right? So it's a 5-line bash script that does Docker run against a set of nodes. That's pretty much what it is. But as applications get more complex and you have bigger needs to deployment and to develop, you need to control your environment a little bit better. You don't want to only run a new container. You want to shut down an old container. You want to set new secrets or environment variables. So we end up adding more complexity to our development tools. And so we go from a 5-line bash script to a 100-line Python script. And the complexity is internalized to the team. The team has to define how much more complexity to add. And the kind of principal approach all those tools have is they're very imperative. They just tell us how they want the system to be. We could add a lot more complexity to the tool, but that would mean making then 1,000-line or multiple thousands of lines of a full-blown program that have control about the whole environment, and we end up doing a mini orchestration. And we have some tools that end up going halfway there, but it's never felt that was a good trade-off for us. We are in charge of developing features for end users, and building internal tooling was not something that we want to invest that much time. It's a trade-off for us because it means that we're not shipping features to users. So, did it change? No, cool. All right, and other big set of drawbacks to our approach is that we use this concept of hosts as pets, right? Infrastructure provides us with a standard set of hosts, and those are fixed. Those runs, we treat them as a finite resource that we have to care for. We even give them names. That's where the analogy to hosts as pets comes from. And if I need to deploy something to a new host, I need to think, do I have enough resource in that host? And that comes the second thing, is manual resource management. I need to know how much resource I have in individual host. And it's not something I can do by myself. I need to also coordinate with the rest of my team. If I need to run an application that requires 500 megabytes of memory, I need to know what host has the memory available. And have to make sure no one else is going to try to schedule something that's bigger or can compete for resource. I have to do all of that at the tool, adding complex to the tool, or adding complex to the person doing the deployments. And we just don't think that was a great trade-off, and we didn't want to keep increasing the complexity in our tools. So the main thing that was missing in our setup was a high-level orchestration system. And being Docker and being the advance that have been seen in the ecosystem, we look inside what Docker has to provide, and we define that we're going to use Docker Swarm for that. Come on. Not working? Okay. So not only Docker Swarm. So Docker Swarm solves the basic ask that we have, something that handles orchestration for us. So we can move the complexity from our internal tools to Swarm itself, and giving us more control about what we want to do and how to deploy to production. But orchestration is one part of the solution, but we also want to centralize how we do user management. We want to make sure that the right people has access to the system. And next, we want to make sure the right people has access to the right level of permissions in the system. And with Docker EE, we can also control that. We can go all the way from the lower level to the nodes that are running, to resource they're running on top of that node. So we can control what volumes a specific container can have access to and what nodes that container can run. So everything centralized in one interface, it's standardized for everyone in the team. So I'm going to head to, sorry, this is my slide. So how we did it. We didn't change anything. And it's just a half joke about our approach was, but our main goal was to add orchestration to our system without touching anything else. We didn't want to just make a change for the sake of the change. We don't think it was a good trade-off if we had to break a functionality because we were trying to adopt Docker. So our baseline was to replace our orchestration functionality, move to Docker EE without anyone noticing. Everything should work exactly the same way. Should be just internal change for us without anything else. So our goal was change orchestration without touching a single line of code, without changing how the code is built into containers, how we do logging, how we do metrics, how we do service discovery, and how we route requests to those containers. That was our goal. Everything else should be the same, so we can be confident that the change we make in the orchestration is good. So we can control, we wanted to have everything else fixed and just change the orchestration layer. So we can have a lot of control about how the move would go, and if we need to roll back, if we had to, we can figure out where the exact source, if there's any problem. So that was our approach, and that was our ask to the infra team. And Brad's going to talk about how infra actually enabled that.
Well, yeah, so like Marcus said, one of our main goals was to enable this transition without us being in their way, right? So like I said earlier, our goal is to be as transparent as possible and let the developers do what they need to do on top of our infrastructure. And basically, the first thing we looked at when we were figuring out architecture for Docker EE was we wanted our developers to be able to move really easily back and forth between them. So we looked at the new SwarmKit stuff, and this was a while back. And we found that there's this cool new thing in SwarmKit called mesh networking. And basically what happens is when you create a service, it gets a port. Each host exposes that port, and when you access that port, you get routed to whatever container is associated with that service, no matter what host it's on. So it's a really cool internal routing mesh thing. There's a few problems with that. The number one for us, just was a non-starter, was we pull metrics from each and every individual container. So our developers build a metrics endpoint into every container, and we go and we scrape that. And with the routing mesh, we couldn't be guaranteed that we were hitting every single container. We just get a random one each time, right? So that wasn't going to work for us too well. And then also we looked at the way our routing was set up and realized that if we wanted to move into the mesh networking model, we would have to basically flip a switch. We'd have to get everyone in a room, say, okay, let's deploy onto the new infrastructure. Okay, are we ready? Push a button and do it. And again, that's not enabling self-service for our developers. They should be able to move at their own pace. So let me tell you a little bit about how our routing setup worked at the time, and we continue to use it, and I'll tell you why. Basically, we have a load balancer that requests come through. It goes through an HA proxy server that routes it to individual containers running on web servers. The servers are running a program called Registrator. Registrator basically listens to the Docker Events API. When it sees a container start up with a port, it takes that container and port, it registers it into console, which is a key value store. Then once it's in console, there's a program called console template running that actually checks console, and if it sees changes, it will go and update HA proxy and reload HA proxy. So basically, a container starts, it gets registered, it gets put into HA proxy, and traffic starts going to it. Really simple, works really well for us. We spend a lot of time tweaking and tuning it, and it's been working really well for us. And so what we wanted to do is we wanted to enable the same experience for Swarm. So that we wouldn't have to change this, and then also we could take advantage of the fact that we could route to both places at the same time. It doesn't matter where the container is running, as long as there's a container with a port exposed on the host, we can route to it. So we went back to our development teams and said, okay, the mesh networking stuff is really cool, doesn't really work for us at this time. What are our other options? They said, okay, well, let me think about that. And they came back to us and said, okay, we have this thing we're going to call host port publishing. And basically, it's publish mode equals host, and that enables the standard classic engine behavior where if you run a container, it gets a port. And so they built that in as one of the first feature requests we had for them, and they built that out, and it made our lives a lot better. So now we figured out the architecture. We know we can do this transition, right? Next thing is, for us, is automation, right? Like I said, everything has to be self-healing, high availability, fully automated. So we started building it out, and the first issue we run into, which you'll probably run into yourself if you want to automate this, is the concept of bootstrapping. So if you've used Swarm, you know it's really easy to get started, right? You go onto one host and you run Docker Swarm init, and then you go onto another couple hosts and you run Docker Swarm join. So really easy for a human to do. It's actually kind of hard for a computer to do, right? So let's say you have really cool automated infrastructure and you're using an auto-scaling group and 3 hosts boot at the same time. How do you decide who runs the init? So the answer, obviously, in computing is a lock. So we already run console, so we use console. It has a locking mechanism. On AWS, you could use DynamoDB. On your own infrastructure, you can use anything you want. But basically, you'll need some concept of locking to get this bootstrapped. Next thing we had to deal with was discovery. So now we've picked the node that's going to do the init. How does every other manager and the worker nodes that are going to join now find that node and join? So we handled that with a load balancer. We put our masters behind a load balancer, so whichever one starts first will get registered into the load balancer, then automatically when the other ones go to join, they join the load balancer instead of the individual node. That's how we do it. You can also use tags if you're on AWS or something that supports tags. That could work too. And then the final thing we had to deal with, and this one was kind of the biggest pain for us, was quorum. Now, so we talked about being self-healing. And with a swarm, the managers have a concept of a raft, a quorum. And as long as you have a majority of nodes that agree, you're fine, right? But let's go through a little scenario where you lose a host, or you do a rolling update and you lose a couple hosts, right? And you expect that when new ones will join, they'll join the swarm and everything will be fine. It's not quite that easy, right? So you have 3 nodes, they're all good. You have a quorum of 3 out of 3, fine. Then one goes down either because it failed or because you're doing a rolling update and you're replacing them or something. So now you have, the state of the swarm is you have 2 out of 3. That's valid, you have a majority, you're fine. A new one joins because your automation joined a new host, but the swarm still sees, okay, I have the 2 original ones, I have 1 down, and now I have a new one. So I have 3 up out of 4. Again, still fine. And then you lose another one. Again, you're doing a rolling update or something, and that goes down over time, or maybe it's a week later, right? But now the problem is you have 2 up, 2 down. You've lost majority, you've lost quorum, and the swarm is now broken. So we have to deal with this somehow. So our solution that we came up with is basically we have a script that runs when the swarm joins, after it joins, or after a manager joins the swarm, and it goes and it queries the rest of the swarm and says, tell me about the state of your masters and your quorum. And if it sees that there's a down node in that quorum, it'll go and query AWS and say, does that machine still exist? And if AWS says no, then we remove it. So you can do a Docker node demote, Docker node RM. And that's how you can fix your quorum and let it continuously self-heal without any intervention from a human. So we solved that problem. Everything was up and automated, and we were running and staging. We deployed a few things to prod, and then we started hitting some other issues. And those are all around resource constraints. So like Marcus said earlier, what we tried to do with moving to Swarm was to take the complexity of scheduling and take it out of the developer's hands and put it into Swarm itself, which is a big win for us, but there are some problems with doing that. So kind of an example, just to illustrate what I'm going to be talking about. When you run a Swarm service, you have the ability to set a reserve and a limit. Now, let's say you have a 4 gig host and you set a reserve of 512. You know your app's going to use at least 512 megs. But over time, apps tend to grow, and so you set a limit of 640 and say, okay, if it hits 640, then kill it. So that's fine. Now you have a 4 gig host, 512 meg reserve. You can fit 8 containers. Swarm will schedule 8 containers if you ask it to. But over time, those are going to grow. And on the right-hand side of that illustration, you can see they've all grown, but they're still less than 640, so none have been killed. But you've run out of memory. So what happens? OM killer gets invoked. The host pauses for a few seconds to figure out what to kill, and then it chooses something and kills it. If it kills a random container, that's okay, right? If it kills the Docker process or a UCP manager or something like that, things get really weird, and you're going to lose your cluster that way. So basically what we did is we went to our developers and said, okay, so we have an idea. When you deploy, we'd like you to set reserve equal to limit. That way we know that what you get scheduled at will always be the same amount of memory that you have and that you can use. So we do over-provision a little bit of memory, but we have a stable cluster. So if you want to replicate this, these are the 2 options. You need reserve memory and limit memory. If you set them to the same value, you'll know that you can never run into an out-of-memory scenario. Or at least almost never. The second bit of this is the system resources. So we've already figured out how to make Swarm not use too much memory for containers, but Swarm doesn't know a lot about the host. So Swarm will schedule up to the available capacity at the time it's scheduling something, but over time, the host itself can use more memory. There's host processes running, who knows what you've got going on. And so the way we solved this was we said, okay, so let's run a service, a global service across the whole Swarm cluster, and reserve, in our case, 1 gig. Depending on the size of your host, you might want to do less, but we reserved 1 gig of memory and just ran a container that sleeps. So it's not actually using the gig of memory, but we've reserved it. So it's basically a buffer for the host. Great, so now we're totally good on resources. Everything is totally fine and stable. And the next issue we have to worry about is permissions. So we run in the AWS cloud. If you run in any cloud, you are probably familiar with the concept of roles. You assign roles to instances that give them access to other resources in the cloud. The problem is that we run containers, not hosts, right? So if we just created a big swarm and gave everyone access to it and said deploy your stuff onto it, and they ended up anywhere in the swarm, then we'd have this problem where we'd have to give every single host every single permission. And our security team is not going to go for that. So basically what we solved this with was basically we said, okay, scratch that. Let's give each team their own auto-scaling group, but join them to the same swarm. Then each engine in those auto-scaling groups, we label with an engine label. And then in UCP, we join them to a collection based on that label. So we create a collection for store, hub, cloud, all that stuff, right? And then we give the developers access to just the collections they need. So they know when they deploy, their containers will end up on hosts that have the permissions that their containers need to access those other resources. And I'll turn it over to Marcus to talk about how they started deploying things on the new systems.
Thanks, Brett. So this is the environment that Infra provided to us, right? At that point, we have UCP and a Docker Swarm ready for production, and we are ready to move our applications into that new system. So one of our main goals was standardize on how we deploy to production. So we had to figure out how to do that. And as much as Swarm is a declarative orchestrator and knows the state of the system, we also wanted to use Compose and its declarative syntax to interact with Swarm. So we settle in every service in our infrastructure to use Compose for deployment. So all the services are defined on a Compose file that defines how each piece of our service should run, and that's deployed with Docker Stack Deploy. So we organized each stack to be a unit of functionality. So it might not be one-to-one, but it might have a couple extra services that are tied to that stack, and that's deployed with Docker Stack Deploy. And being a Compose file, we just store that in version control. We just store in our Git repository, so that can go through a code review process. So developers in the team know the change that's going on. And Compose being so common and understood by us, as we use that for local development as well, it's very easy to onboard people. Everyone that uses Docker has a high chance of having used Compose in the past. So it's a very easy tool for us to get familiar with. And I think it works really great. And you can see just an example of a simple application that exposes some ports and environmental variables. So that's how we get the application initially on the Swarm. But how we do control all the complex update logic? Application is not going to be run only once, right? You're going to have to do updates to that. So how do you control? So using Compose, we can encode all that logic into the Compose itself. So here's an example. It's part of the deploy configuration for Compose of the update configs for the app. So the same Compose that defines how your application should be also defines how the application should be updated. So in that example, you can configure how fast the update should be and how parallel. If you're running like a 200 node replica, how fast the update should go through and what's the parallelism of that. And you can also define what to do if there's a failure. Should that roll back? Should stop? Should pause? And you can configure everything from the same declarative syntax. In the same way, you can go through code review. If you want to do some change to the deployment model, everything in the same syntax. And talked a little bit, and automate rollbacks can be part of that as well. So now you know how to deploy your service to production and how to update your service in production. You also have to make sure that your service is running on the right nodes, right? Because you have all the permissions attached to the node. So we use the feature in Docker EE to deploy a service to its right collection. So we can inherit all the permissions that attach to the collection. So once we define a label that marks the services belong to a specific collection, Docker EE is going to resolve the collection and apply all the correct permissions to that. So if you have a pool of nodes and only a few of them have access to that collection, the service is only going to be scheduled on those nodes without having developer having to know about individual nodes. Everything managed, centralized by Infra. So that's a great improvement for us. And I think one of the things that was thing that we felt the most was the ability to completely decouple how our application is deployed from the host they're running on. And it just made it much easier for us to think of applications as completely separate from the host. We don't have to worry about individual nodes on the cluster as as a unit. For us, it's just a pool of resources that are available to each team, and they just only need to think about that pool of resource as abstract. We don't worry about if they're running 10 instances or 3 big instances. Everything can be done by infra, and infra has full control about the underlying host. For us, it's just how much memory and CPU resource we need. That's the only thing we care about. And that delivering the promise that we don't own nodes, we don't own the infrastructure that are running our containers. We only run the containers that run on top of that. So that creates that great separation of concerns. And just to give an idea of what kind of improvement we're looking, and compared to how we used to run things in the past. In the past, if infra needed to replace a host, and if you're running in a dynamic environment, you're going to have host failures, you're going to have to replace a host because of hardware maintenance or any other reason. So infra would get a note from our cloud provider that a node needs to be replaced. And they would open a Jira ticket with us and say, hey, I need to replace node A. Developers in the team would go and say, oh, okay, so what's running on node A? They will do a Docker PS, find out what's running, and then find out who owns each of those applications. Luckily, it might be in the same team, but there might be a developer that owns one application that's in Hawaii, and you have to figure out how to move that to the new host. So you go, it might take days, sometimes weeks, and it's all very high touch, right? So it doesn't really match in our goals and our philosophy about how we should run infrastructure. So how is host replacement for us now? As a developer, I don't know. I don't care about how that happens. For an infrastructure perspective, they can just go replace a node. Swarm is going to take all the tasks that was running in that node, move to the remainder of the cluster, and infrastructure can add a new node to replace that. And they can do that throughout the whole cluster. And they can decide if they want to go and upgrade our instance to a new version. They can just do that without any coordination from developers. Everything is done without us being paged or getting tickets. Everything is very transparent to us. And that's one benefit that's very easy to understand, very easy we felt the benefit right away. But there are other benefits that we came from that process. It's very easy for us to scale our applications up and down depending on the needs. If you're running a Docker Hub, there's a lot of spikes in traffic that we have to deal with. We need to scale up. Sometimes we have to scale down when the demand goes down. And we have a very easy way to do that. And we have the whole cluster available for resourcing if we need to. And standardization is something that has been a great benefit to us. Every developer in every team knows exactly how an application is deployed. And they can go to the same dashboard and see how an application is deployed, what configuration is being used, how it has been deployed, what's the last time it was deployed, everything in the same format. And standardization is great by itself, but the fact that we use Docker to do all of that also means we benefit from all the improvements that Docker is doing and the community is doing to all those tools. So we have a standard set of tools developed by Docker that help us do all the deployment. Everything that we deploy is done through Docker native tooling. So just to give just a overview where we are now. As of last week, every service on the Docker platform that you interact on a daily basis is running on top of Docker EE. So every time you do a Docker pull or a Docker push, it's going to be handled by a service that's running on our production Docker EE cluster. We're running around 80 nodes for all the workloads that we have in our infrastructure. That's backed by around 60 Swarm services, so all the individual microservices that we run. We're a total of 1,000 tasks. If you're not familiar with Swarm concepts, a task corresponds to a container that's running on an individual node. And they can get rescheduled. So as we do multiple deployments a day, that means we have a lot of new tasks being launched all the time. We always have tasks being run. We always have tasks being rescheduled somewhere. So there's a lot of, our clusters being used a lot, and we have a lot of task rescheduling and movement. So we're really making use of all the features in Swarm for that. And Brett's going to talk about how our work doesn't end here, how we're making this better.
Cool, thanks. So one of the goals in doing all this was not just making our own infrastructure better, but with this dogfooding project, as we call it internally, the big goal is to improve Docker EE as well. So the first thing we're doing is During this process, my team wrote a bunch of internal documentation on what we felt were best practices for ourselves and how we run things, and just worked well for us. And basically, we took those to the customer success team, and we're building out articles on all this stuff now. So things like managing resources that we talked about today, the memory limits, that kind of thing. Provisioning and automation. A lot of customers asking, like, what's the best way to automate this kind of thing? And we've done all that. And logging and monitoring is a big one for us as well. So you'll see a bunch of articles about that on success.docker.com, hopefully very soon. We'll see. And the second most important thing for us is product guidance, right? So we're an in-house customer, which is really cool for our developer teams who build these products. We're literally across the hall from them. If they have any questions, they can come to us and we can talk about maybe the best way to do architecture. If we have problems with our cluster and they need to help debug something, usually with customers, they have to go back and forth through solutions architects, that kind of thing, send logs, etc. We can pull a developer over and have them sit down and say, okay, well, let's look at this and figure out what's going on. So that tightens the release cycle for us to fixing bugs and things like that. And through this process, we filed about 35 feature requests. The first one of those is host port publishing, which we talked about earlier. And there's a bunch more that are coming. And then, of course, we're a canary, right? So we run every release candidate of Docker EE before it gets out to the public. And in doing so, we found a few bugs. We filed about 50, obviously not all of them major. And most importantly, we're customer zero, right? So everything goes through our production environment before it goes out to customers. And I'm sure you saw the keynote yesterday and the Kubernetes announcement. And so, of course, we will be the first customer running Docker EE with Kubernetes in production. And that's all we got. We're going to take questions. If you could please find a mic so that the recording gets all this stuff. Thank you for your time. Thank you for staying around for the last session. We really appreciate it. Thank you.